So what I'm thinking is that if this hair gets long enough, I can just wrap it all the way back over and fill this in again, and it'll be normal. Anyways, let's take a look at this problem here. This is from week 4. It's an angular momentum problem, a conservation of angular momentum. This is the 33.3 problem, if you're kind of playing along with the class. What we have here is a 12.5 kilogram child, a good tossable size. And they're standing at the center of a 125 kilogram playground merry-go-round thing. Those are kind of the death traps of old where you would hook like a motorbike to the back of it and then just kind of spin it really fast and the kids would fly off. They kind of got rid of them everywhere, but we can remember the old days. But this thing rotates at 3.1 radians per second. So this here is an omega. The child moves to the edge of the merry-go-round. What is the new angular velocity of the system? Model the merry-go-round as a solid disk. So, what do we have here? Well, to begin with, let's kind of draw a quick little picture for us. To begin with, we have a merry-go-round, and it has some radius, and let's just ignore the radius for right now. It's just irrelevant. But this merry-go-round has a mass of 125 kilograms, and sitting directly in the center of it is a child. And that child, we'll call this MC, has a mass of 27.5 kilograms. Now, if we have an initial angular momentum, which is up here in green, the 3.1 radians per second, and we're looking for the new or the final angular velocity of the system as the child moves from the middle out to some point, our angular momentum is going to change, or our angular moment of inertia is going to change, and our angular momentum will be conserved here. Excuse me. This means that the initial moment of inertia times an initial angular velocity is going to equal a final moment of inertia multiplied by a final angular velocity here. Now, looking at this scenario, our initial moment of inertia is actually going to just be the mass of the merry-go-round, and multiplied by the whole 1/2 mr squared. We're not going to include the child's mass initially in this merry-go-round problem because the child is initially sitting right here in the center, and that means that if we were to model them as a point mass, which we're going to do, their distance from the pivot point, which is the center, is 0. So the moment of inertia for any point on this merry-go-round is going to be that of the disk, and the disk is 1/2 times the mass of the merry-go-round, 125, times the radius squared, and then it's going to be plus the mr squared for the child. So this is like the m child r squared. But since the child is sitting in the center of this, that r is a 0, which means we get nothing here initially. So this is just our initial moment of inertia. Our final moment of inertia is going to be the 1/2 125 r squared, but this time we actually will have the mass of the child because our child has kind of drifted off over here. So now we're going to have an additional 27.5 r squared. And in this case, that r is, let's see, where are they at? The child's at the center. The child now moves to the edge of the merry-go-round. Okay, so they just move out to the radius, which we still don't know what that radius is, but that's where they've moved to. So let's take a look at how we're going to solve this problem. Now, a helpful hint to this, we do not know this radius, and we're going to see in a second that the radius does not matter. It's actually going to go away. But if you feel uncomfortable doing this algebraically and you're like, oh no, I need to know the radius, just put a dummy number in, like 1. That'll make your life easier. But I'm just going to leave it as r squared for now so you can kind of see where we're going with this. If we come over here, we start plugging into these two equations. We'll do this in pink. The initial moment of inertia was 1/2 of 125 times r squared. And then the initial angular velocity we had was this 3.1 right here. So this is times 3.1 radians per second. This is going to equal the final moment of inertia, which we have as the quantity. This is a kind of bigger quantity. 1/2 of the 125 r squared plus the 27.5 r squared. So that's the merry-go-round plus the child. And then this is the final moment of inertia, and this here is what we're solving for. So if I kind of look at this, one of the things I might initially note is that both of these terms here have an r squared in it. What that's actually going to allow me to do is I'm going to be able to pull that r squared out. I can factor it out of the problem. And when I pull this r squared out, you know, if I think about pulling it out, I'll just stick it over here. It means I can erase these. With that r squared being out of here now, I've got an r squared on the left side and the right side, which means these are going to divide each other away. Okay, so the r squared does not go away. Whatever. The r squared doesn't matter here, so we quickly see that mathematically. At this point, now we just have 1/2 of 125 times 3.1. So on this side, I'm just going to multiply all this together to get some number here. So this is just some number. Let's just pull out the calculator, figure what that is. So 125 times 3.1 divided by 2. This is going to give me, on the left side, 193.75. And this is going to equal some number here times omega f. So let's just put this together real quick. This is 125 divided by 2 plus the quantity of 27.5. This is going to give me 90 on this side, omega f. And at this point, we just need to divide out by 90. Shing. So 193.75 divided by 90. We're going to get something a little bit more than 2, it looks like. And we find that our final angular velocity is 2.15. Because this is an angular velocity, it's in radians per second. So there's our answer right there. So not too bad. We are just employing the conservation of angular momentum. Whatever momentum we had initially has to be what we have at the end. Remember, angular momentum L is equal to just I omega. And so in this case, our initial angular momentum equals the final angular momentum. The kind of trick to this problem was that we had to try to figure out what these moments of inertia were for the merry-go-round in the beginning and the merry-go-round after the child moved outwards onto it. And then it was just math from there. So not too bad. With that, the problem's finished. Take it easy. I'm going to keep working on this mega hairdo that's just getting totally crazy and out there. But I'll see you next time. Adios.